So looking at page 53 in the Unit 3 packet, talking about the central limit theorem here. This one's an interesting concept because what we're dealing with here is the idea that we're taking a population, creating samples from that population, and then working with those individual samples one at a time, and then seeing how they interact with each other collectively. And in general, the idea is to use that information to draw conclusions about the entire population itself, but there's a lot more to it than that. But I have found over the years that just telling people, here's the rules, and then going from there, it never really ended well. So what I like to do is take you through a quick little mini activity and kind of show you what these relationships really kind of work out to. All right, so we're actually going to jump right down to this little section at the bottom here where it says, given a population consisting of the numbers 1, 2, 3, 4. All right, so the population, I'll just jot it down over here. We have the numbers 1, 2, 3, and 4. Find the population mean and standard deviation. All right, then it gets a little crunchy after that, so we'll cross that bridge in a second. But the population mean is just going to be the average of these four values. All right, so what I'm going to do is I am going to input a set of data here, just the numbers 1, 2, 3, and 4. All right, not the kind of thing that you would actually need to use the calculator for the mean anyway, but for the standard deviation, we tend to want to do that. All right, so mu, if I go to functions under stat, we'd find the mean of the data stored in x1, and that's 2.5. The standard deviation, that's the population standard deviation function, STDEV-P, population standard deviation P, population. So x1, all right, again, that's where the data is. So 1.118, all right. So mission accomplished, or at least that mission. Then list all possible samples of size 2, all right. So what that's telling us is that if we take the numbers 1, 2, 3, and 4 and put them into 2-unit arrangements, what would those arrangements be? Well, our samples would be 1 in itself, right? This is assuming with replacement, right? So 1 and 1, 1 and 2, 1 and 3, 1 and 4, 2 and 1, 2 and 2, 2 and 3, 2 and 4. Probably could have wrote those numbers faster. 3 and 1, 3 and 2, 3 and 3, 3 and 4, 4 and 1, 4 and 2, 4 and 3, 4 and 4. And that would be our list of possible samples of size 2. All right. So what we want to do is we want to average each possible pairing. All right. So we're going to average each of these. All right. And so we would do that down the line. That I think I do have to copy paste. Give myself a little bit more space here. Smidge that over, smidge that over. Then it's just the commas. You never truly realize how terrible your penmanship is until you duplicate it many times and see it in action. So we'd average all of these values together and make a new list out of those averages. All right, so that's obviously fairly challenging in terms of the monotony of it and even the tedium. But those samples will have averages, and you could probably do it in your head. 1 plus 1 is 2, divided by 2 is 1. 1 plus 2 is 3, divided by 2 is 1.5. But you can use technology if you want. It really doesn't make a difference. All right, so 1 plus 3, 4 divided by 2 is 2. 1 plus 4 is 5, divided by 2 is 2.5. 2 plus 1 is 3, divided by 2 is 1.5. Then 2, then 2.5. You notice the trend here, then 3. So the first grouping started off with a mean of 1. The second grouping started off with a mean of 1.5. The third one will start off with a mean of 2, so 2.2, 2.5, 3, and 3.5. And the last group will start off with a mean of 2.5, so 2.5, 3, 3.5, and 4. So what we would be looking to do here is find the mean and standard deviation of this new group of data. All right, so if I'm finding the mean of this list of x bars, I would be calling that mu sub x bar. If I'm finding the standard deviation population of this list of x bars, I'd call it sigma sub x bar. So what I can do is put all this stuff in a new list. I could put it in the same list, just in the y1, or I could actually just make a new table. It's x1 now. I'm sorry, x2 now, but that's fine. 1, 1.5, 2, 2.5. The next one, it's going to say 3, but I needed to go back to 1.5, so I'm going to make that adjustment. 1.5, 2, 2.5, 3, then back to 2, 2.5, 3, 3.5, then 2.5, 3, 3.5, 4. All right, so assuming I typed those values in correctly, I can now find the mean. That's all in x2. And look at that, it's 2.5. Just like it was for the entire population. Oh, that looks terrible. And just like it says up here, mu sub x bar and mu are supposed to be the same thing. All right. Now for the standard deviation for the population, all in x2, I have about 0.791, ballpark estimate. That's not a 7. All right, well, that's certainly not the same as sigma, but it wasn't supposed to be. All right, so they told us up here that sigma sub x bar should be equal to sigma divided by the square root of n. All right, so let's see about that. So sigma divided by the square root of, well, samples of size 2. So that's telling us that n is equal to 2. So sigma over the square root of n should be about 1.118 over the square root of 2. Et voila. 0.791. All right. So what we get from this are a couple of things. And when it comes to rules, I mean, we have the same experience in every topic in this entire course as we work our way through trying to understand formulas and things like that. It always comes down to, when do I use this? All right, and so that's what we're going to learn in the next couple of pages. But what we just discovered is that if we break our population up into infinitely many samples, now in this case there's a finite number of samples, but you know, the larger the number of individuals within the population, the more prohibitive it becomes to list out all the different possible samples that could exist. You know, we got the numbers 1 through 4, and it already took us like 10 minutes to do. Can you imagine if it was a list of numbers 1 to 1,000? It'd take you the rest of your life. All right, so obviously not something you want to do, but what we just determined is a way in which we could find the mean and standard deviation of the list of sample means that we would get if we were to break up that population into these different samples and find the average of each sample. So that's got to be worth something, and that's what we're going to figure out in the next couple of pages.